Let's definitely get started. It is good to see a lot of people here today, and I know that's not just because we have a quiz. We're still in the middle of that transition in looking beyond just assembly level issues. Today's quiz will still be about assembly, but looking at the general performance equation and the implications of that equation for understanding microarchitectural design decisions. And certainly, um, the actual math we're doing, the actual arithmetic, isn't all that difficult, I don't think. The analogy I tried to draw on Monday was to treat these kind of questions like they were physics questions, but the easy kind of physics questions, where to know if you're going in the right direction, one approach to take, and the approach that I take, is to consider the units of the quantities that you're attempting to measure and analyze. And when you do that, the hope at least is um, that you get something at the end of the day that makes sense. So we did that meters per second example. We're going to get the same kind of example today with regards to the various quantities that we can measure about a computing system. A lot of this is a little vague in parts. I think it's chapter one. It's introduced in the textbook before any MIPS details are discussed at all. But we can start to take it to a more precise level. So where we left off on Monday was looking at this understanding of what it means to have performance, and we came up with different definitional terms that we can use. But by and large, performance revolves around the time it takes to accomplish something, right? So if a question is asking you about this CPU's performance in general, your answer should be in terms of time or ratios of time or increases of time, things of that uh, category. And so we have different ways of breaking down that basic performance equation, but in general, the end result in terms of the units that we're calculating should be in terms of time. And the most basic way of doing it is to just consider execution time as a function of the clock rate of our CPU. This was the quick version of the breakdown that we talked about on Monday, which was, we have all this work that we need to get done potentially in a single cycle. That's our foot cadence. That's how quickly your circuit can get something done in a period of time. And then we have the various paths that dictate what that clock cycle needs to be. What the critical path is, the longest path. We have to make sure our clock cycle is long enough to support that. So, in terms of our execution time of a piece of software, it's going to be a function of that amount of time associated with a single cycle. So, we can start with by just breaking it down and just saying our performance using the basic performance equation, it would be measured in seconds. And certainly it's performance of something. And in this case, we'll say performance of a program would be measured and would have units of the type seconds or some time scale where there really isn't a secondary unit, but you can think of it as seconds for a task, or in this case, maybe seconds to run a program. Which, if we care about the performance of our computing system, that is one way we could measure it. How long does it take to run this program given this set of assumptions? And we have a way of breaking that down. We know, for example, given our underlying implementation, we have this clock frequency, we have this clock rate, we have this critical path of our underlying implementation, and that can be part of the equation, right? That can certainly tell us, our clock rate tells us, well, how many seconds does it take for a single clock cycle in my underlying implementation? Right, that's the same as our clock frequency, right? Frequency is measured in cycles per second, so the inverse of that, right? So we said 10 nanoseconds is 100 megahertz. That's the same quantity here. This would be measured in maybe nanoseconds or picoseconds or something like that. But it's seconds per clock cycle would be the quantity we would be interested in measuring for this part. And then to get from that to seconds per program, again, if we think of it in terms of our easy physics units, we have seconds already. We would then need to have some way to relate that to how many clock cycles does it take for a given program. And if we do that, the units kind of break down properly, right? Cycles and cycles break down. We wind up with a quantity that's in terms of seconds per program. Measuring the amount of clock cycles for a given program is a pretty awkward thing. It's not a way we typically think of programs as they're executing. We're not sitting there with a tool that allows us to count clock cycles, and we're not analyzing it usually in terms of that quantity of takes 10,000 clock cycles for this program. Sometimes, and we've done this a little bit so far, we've tried to estimate that, and that can sometimes be useful. But that was with a pretty simple assumption of maybe one clock cycle for a given instruction. And we can certainly then break down this quantity more of cycles per program as being a function of the number of instructions we know that our program would need. That's something we should be able to estimate and or measure. And that's we talked a little bit about dynamic instructions versus static instructions. That would be our dynamic instruction count, right? That would be how many instructions does our program take to execute? Measured in millions and billions and trillions, right? In a very large number potentially, even for some of our simple examples, right? You can write a 5-line piece of code that executes 10 billion times in a very trivial manner. That's our dynamic instruction count here. And then if we just look at the units and how to cancel that out, the next quantity that would be relevant for this performance equation would be we need cycles per program, we have instructions per program. Consequently, we would then also need a quantity referred to as cycles per instruction. And that turns out to become a very important one for our purposes as computer architects or those who are trying to survive a computer architecture course. And the units kind of cancel out there, right? So from seconds per program, the time it takes to get something done, that is important to us. It is ultimately what we measure in terms of our performance. In terms of analyzing it, we would have some quantity that's sort of a given as part of our design space decisions of what's our clock rate, how fast of a clock can we do, and then we can break that further down the number of clock cycles required by our program by looking at what's our dynamic instruction count, as well as generally what is our number of cycles needed per instruction. And this is such a common quantity, and it's just literally cycles over instructions, cycles per instructions. We hear it referred to as CPI very often. So that if you see that term already in chapter 1, CPI, that's literally just the ratio of number of clock cycles per a given instruction, and it tends to be an average. And we'll see why that's an average. The reason this number isn't a trivial number to analyze is based on the very high level analysis we were starting to do on Monday, which was we have potentially a single cycle to design where CPI would be equal to 1. So your project part B processors, you have a CPI value that will be equal to 1 by design. But as we start to break that assumption, relax that assumption with regards to how we split up the data path to implement the same set of instructions for our MIPS ISA, we would then potentially have a CPI of greater than 1. We talked about, and it was pretty brief, and we're going to keep coming back to that for that critical path, load word is what's using all of those functional units. And it's the only instruction class that is using all of those functional units. And if we were to break down our load word functional units into 5 different cycles here, the CPI for loads would be effectively 5. At least that's one way to visualize what would be happening here. Because it has to get through every one of these steps. Every time we have to cross the boundary of writing an update to a register, that would be an additional clock cycle. Load words would have a CPI of 1. But then we also talked about on Monday how if it were a jump instruction, well, jump doesn't need to do hardly anything at all, right? We have to fetch it, maybe we wait a cycle. We then have to decode it, maybe we have to wait a cycle. But at that point, we know we're done. It's a jump. We're not doing any math. We're not we're not having to read register files. We're not having to do anything other than just update the program counter at the end of that instruction. Our CPI for a jump could be 2, maybe 3 cycles. That would result in an instruction mix in which, depending now on what our program is actually doing, you would have a different value for your CPI. So that becomes a pretty powerful thing to analyze and to reason about because it not only changes based on architectural decisions. If I add another register, that may improve my clock frequency, but it may negatively impact my CPI because it may require more clock cycles to get an instruction to complete, to be done. But that CPI is also impacted by your instruction mix potentially as well. If I have a code that is just very jump heavy, just for this example here, we may wind up with an instruction mix with a relatively low CPI. But if I have a code base that's extremely load word heavy, and one could hypothesize a scenario in which we're trading off jumps for loads in some analysis we're doing at the algorithmic level or the compiler level, we may wind up with a relatively very high CPI for that same task we're trying to accomplish. So you'll see this term CPI a lot because it is impacted by everything, potentially by choice of algorithm, certainly by choice of compiler optimization and instruction mix, and certainly, although not on a daily basis, on a generational basis, it's affected by the microarchitectural design decisions we make when determining how many cycles a given instruction are requiring, and then consequently what an average CPI would be for a given application. CPI, lower is better generally. It's exactly the same as a term you may have read if you're looking at, either marketing or technical breakdown of modern microprocessors, which is just IPC. And maybe you've seen that term more so than CPI if you look at a review of AMD's latest processors. It's the same thing. In fact, well, it's the inverse, right? So CPI is cycles per instruction. How many clock cycles on average does it take to execute a given instruction? Our best case in 381 is a CPI of 1.0. That's our goal. If we can keep it at 1.0, we've done a pretty good job. Modern microprocessors, the CPRE 581 processors, can achieve a CPI of much less than 1. And for that reason, if we want bigger to be better, we use the metric of instructions per cycle. It's the same thing, it's the inverse, right? How many instructions on average can I complete in a given clock cycle is what IPC is attempting to represent. And so a very low CPI would correspond to a very high IPC, and that's one reason you see that term. But they're equivalent. They're measuring the same exact thing. The relationship between getting an instruction done and a number of clock cycles, which is impacted by all these factors: what instructions we use, how we break down the microarchitecture, what even potentially the compiler is doing of choosing less expensive or versus relatively more expensive instructions to accomplish a given task. I promised a quiz today, and I know that's why we have 116 people here today. So let us pause here and open up Canvas. I should have it open and available for us here to take it would be the week 6 quiz, but which would be listed as quiz number 5, right? We had a slightly larger quiz last Wednesday. So you would go into Canvas for week 6, and you'd be opening up quiz number 5 here. It should be open and available, and the code is there. It seems like people prefer if I just type it in the chat, so I will type that in the chat. So you can copy paste it if you don't believe me when I say it out loud. This is first third of the semester questions. It's a final sanity check for me to know, okay, we had an exam, things went well for some, things went less well for others. Do we know the basics? And that's what this quiz is attempting to accomplish. I had promised to wake up everybody who had fallen asleep at this point in the lecture. Um, Wake up if you haven't. Let us take one more minute if we can. And as I've always said, these are certainly just participation quizzes. So the questions are there in part for you to see, okay, here's what I know or what I don't know at this point in the semester. And they're there for me as well. It helps me check my assumptions about how things are going, who's got things figured out, and who needs a bit more assistance along the way. So let's just take one more minute. So William, I'm going to pick on you. Yes, you. You're the only person who keeps your webcam on, and I appreciate it because it's the only way I've any. Otherwise, it's completely a blank set of names I'm just talking to here, and it makes me very self-conscious. I'm not requesting anyone ever turn on their webcams, but I appreciate you for having yours on, but you have that extra responsibility of if something's really wrong or confusing, you have to really make quite a face or let me know because that's the only visual feedback I have this entire semester. So your expressiveness is very important. And if there were a day, unfortunately for you, that you weren't able to make it to class, it would be immediately obvious to me as well. So I guess you're really responsible for being here every single day. Um, if there was a question that said add UI, that was a typo. So if it said add UI on the quiz, that was a typo. That was not intentional. I'll take a look at that offline. Um, okay, so let's circle back here. And again, quiz is just participation. So you've participated. Congratulations, you have succeeded today in terms of having participated in the class. So don't stress. Um, okay, so we have the performance equation, and we have our way of reasoning about it, which is really about CPI. And actually, I can actually pretty quickly just jump past these next couple of slides because it's exactly what I just mentioned. That performance is measured in time. That's one of the big important takeaways here. Performance is always measured in terms of time, and it's performance for a task that we care about. So how many clock cycles it takes associate for a program multiplied by its clock cycle time, or that's equivalent to dividing it by its clock rate. We'll separately briefly talk about a complementary challenge of measuring performance, which is really benchmarking performance. I do know that a lot of sort of computing hobbyists, people who care about latest and greatest computing hardware, care a lot about these sort of things. But that's actually a very hard problem to solve, which is what is a representative workload for a computer to be able to generate a clear, quantifiable answer to is this computer better than this other computer? The answer always tends to be within equivalent class computing. It depends, and it depends on what the application we care the most about is, as to whether or not one given computer is better than one other given computer. Benchmarking is actually a very hard problem. We can throw lots of workload at a computer and measure the performance associated with the number of clock cycles it takes to execute. To the extent that's truly representative, that's not something we can easily self-contain and say this is a representative workload. If you buy this computer A versus computer B, you'll have a faster computer. That's a very hard thing to be able to answer in a definitive way. But there's been a lot of activity in generating useful benchmarks for exactly that purpose. Ultimately, though, I would say the takeaway is for this performance equation to be meaningful, for us to measure the performance of something important, it has to be something that is relatively real world, not entirely synthetic benchmark. a benchmark that allows us to get some idea for this class of workloads, that time associated with executing it can be meaningful. And consequently, a speed up in that time, an improvement in that time, can also potentially be meaningful. So before we jump over to the quiz, I also mentioned this as well. So clock cycles per program is not an easy thing to necessarily measure, but instead we can measure the number of instructions required to execute a given program, and then multiply that by that CPI value, which is used very often for estimating for understanding performance. That is the average number of cycles required to execute the instruction. And it's going to be an average because in many processor implementations, and really in every processor implementation beyond our Project Part B implementation, the number of cycles for a given instruction is going to depend somewhat on what the instruction is doing. It's not a fixed quantity. Um, there's a little bit of a separation in this class in which we do artificial physics style problems where I just say the CPI is 1.4, but we never design a processor for which the CPI is 1.4. So we learn some of the tools to be able to do the arithmetic associated with understanding performance. It's a little bit separate conceptually from what we're actually able to build, which is a couple of very specific cases with specific CPIs associated with them. Um, but it is in and of itself a very useful metric to know about a given architecture. So drawing on that equation of our clock cycles is just our instruction count times our CPI, we have, I would say, a somewhat more useful and workable equation for overall performance of a given application. You'll see the textbook break this down in a few different ways, but it's all roughly the same, which is we have performance measured in time. That's a big takeaway. If you wind up with your performances measured in terms of instruction count, that could be okay, but you still then have to ask the question, well, does my instruction count matter, or is it really the time it takes for those instructions that really matters? So performance in terms of execution time, excuse me, performance in terms of time, which we can break down by, I would call that IC, or instruction count. That's what instructions corresponds to on this slide, multiplied by our CPI. So instructions per program multiplied by the average number of cycles per instruction, and then multiplied by the clock cycle time, or that's equivalent to dividing by the clock rate with our implementation. So if our goal is to improve the performance of something, right, we don't have to be vague about it anymore, right? To improve the performance of something, that means lowering the execution time. Less time is better, right? We want to have it take fewer number of seconds to execute a given application or set of applications or benchmark of applications. And according to this equation, there are really only three ways to do it. We want to improve performance, and that's our breakdown of the performance here. We have our instruction count. So if we want to make that value on the left-hand side of the equation smaller, we have to then also reduce our instruction count. That's one way to do it. So one way to improve performance, and I think that makes some intuitive sense, would be to decrease the number of instructions required for our program. We think of the hardware-software stack, of which as computer engineers and software engineers and the occasional double E in this class, cybersecurity as well. We look at the entire hardware-software stack, and there's quite a few levels along the way that allow us to improve upon our instruction count. Algorithmic optimization. All of ComSci 311, those of you who get the opportunity to take that class, is about reducing the computational complexity of an implementation. And we use big O analysis to kind of estimate what type of improvements would be made. But in terms of performance, that's ultimately due to decreasing the instruction count of our underlying implementation. Likewise, all the compiler optimizations, and we've just briefly touched upon what a compiler can do. We haven't talked at all about how a compiler can do those things, and that's okay. But that's really about decreasing the instruction count associated with our implementation. That's one way to improve our performance. CPI is our average clock cycle per instruction. We can decrease that, although it's a little bit trickier. If it's associated with our instruction mix, we can potentially do things at either the algorithmic or a compiler level to change our instruction mix. The example I gave was reduce the number of load word instructions and replace them with jump instructions, or something with lower CPI instructions for the equivalent number of higher CPI instructions. Otherwise, maybe that's an architectural decision, which we can still do, but that happens relatively slowly. In terms of when we release new architectures, we make different design trade offs of how we pipeline the design, how we split up the clock frequency, the critical path to be able to change our CPI for a given application and given instruction mix. And then finally, the other way would be to increase our clock rate. If we go from a 2 gigahertz to 4 gigahertz implementation, all else being equal, we should have roughly twice the performance, right? That's all else being equal, but that's the tricky part of this performance equation as well. It is very hard to change any of those three components of the performance equation entirely in isolation. Changing one tends to have an impact on the others, at least one of the others. The example we already saw but didn't mention it as such is that we wanted to split up our critical path. And why do we want to split up our critical path? Well, because we wanted to reduce our critical path. That would be one way to increase our clock rate. That should improve performance. But in splitting up our critical path, we've made our CPI potentially worse. So for any given design decision in isolation, because you're balancing one of these factors typically against another, it's not that easy to say that, yes, making this design decision will improve performance overall. We can reason about it, we can estimate it, we tend to have to measure it at the end of the day to know for certain that this design decision is a good one or not. And sometimes, even the people and the teams of thousands who are part of the design performance projections teams at companies like Intel and AMD, they get it wrong sometimes as well, right? They make certain assumptions about what clock frequency will be possible within a given thermal or power envelope for a design, and what the resulting CPI would be for those design decisions, and they get it wrong occasionally as well. It is not a trivial thing. The math we do for it is straight arithmetic, and the homework questions you'll get about this are relatively trivial because we can't design a whole new processor each time. We can only sort of reason about what a processor could look like. But the actual trade-offs involved are not trivial at all. I'm seeing some questions about that last question on the quiz, and it's okay to move on it, but move beyond it. The last question was just asking about, and there was a exam question about this as well, about branch target addresses. What does that mean in terms of the encoding? And it was asking literally what would the immediate value need to be for that instruction to be able to branch backwards. It's something we've talked about a couple of times. I would just say, that this quiz was to determine, post exam, are you caught up with that kind of MIPS assembly content? If you got the answer off by one or something, that's always fine. That happens to all of us. If the question didn't make any sense, that's probably a bigger issue that we should probably discuss. Lost my train of thought here. Okay, so the textbook questions that you get about the performance equation tend to be, I won't say trivial because you're the ones who are going to have to work on them, and it's easy to grade, trivial to grade, but they're relatively straightforward. It's just word problems with regards to how do I take the description of what's being given to me and convert it to the components of the performance equation. So this is straight from the textbook question, and you can even see it's dated like many of the textbook questions at the end of the chapter are. So if we have a mobile Intel Pentium 4 versus an Intel Pentium M, that's a quite dated example, but it doesn't change how we analyze the performance equation here, where we know the clock frequencies of the two. That despite the relatively large increase in clock frequency between one architecture and the other, when measuring on a meaningful workload, we determined that the performance of the quote-unquote faster processor is much more modest than we would expect it to. So the question would be asking, how did this happen? And in order to do that analysis, all you would do is take those components, and I could walk us through this if we need to. I think in the interest of time, I won't. But you would just be plugging that into the performance equation for both. We're told everything about this performance equation save for the CPI. We're not told the execution time in terms of seconds, but we're told the relative execution time, and we're told that one is only 15% faster. So we're being told that there's a 1.15 ratio between the time associated with executing this benchmark set on the Pentium 4 versus the mobile Pentium M. So that is given. We don't know the actual time, but we know the relative time, and that's all we need to know to be able to answer this question. We're also told the clock frequency, so that's also a given, and the ratio between the two we can easily calculate. We're not told the instruction count for this question, but I think baked into this kind of word problem, and this is where it becomes maybe non-trivial, and if you're answering this on an exam and time is desperately running out, state your assumptions and move on, as always, that if it's the same general architecture for which there's just microarchitectural changes that are made, if it's the same ISA, so it's running the same instructions for one processor A and processor B, then if that's the assumption, then the instruction count would also be the same for both. That is not stated explicitly. I think a slightly better worded question would be assume the instruction count is the same. But it's running the same applications, targeting the same ISA. The instruction count should be the same for both. We also have to assume it's the same compiler and the same compiler optimizations. This problem is only workable if we assume that the instruction count is the same. And then to be able to determine what the relative ratio of CPIs would be, would just require plugging that in and then solving for the ratio of one CPI-A to CPI-B for those two processor designs. You'll get plenty of examples, starting with homework number 5 of working through those. If we need to come back to that at a later lecture, whether it be Friday or next Monday, we can do so. Ultimately, these aren't terribly interesting problems to me. Understanding our CPI as a big picture concept is more important than making sure you can plug this in correctly. And I mentioned that again, the CPI is an average, and it does depend on the types or classes of instructions that you are supporting, and so we can actually measure that average CPI, right? Um, Based on for the number of instructions that are of a certain category, here's the CPI for that category of instructions, and ultimately we get what would result in sort of a weighted CPI. That we would be told or we could measure that for the load word instruction, it's always going to take 5 cycles. But for the jump instruction, it's always going to take 2 cycles. We don't just average those together and get an average CPI of 3.5. It's a function of the relative instruction counts for a given program we're wanting to measure what the average CPI would be in that case. And that's all this is trying to illustrate here, that as we're trying to ultimately calculate the number of clock cycles, we could just measure the CPI for a given instruction count class and multiply it by the instruction count for that instruction class. So we have 5 for load words and we have 100 load words, and we have a 2 for jump, but maybe we only have 1 jump in the entire program. Our average CPI is going to be relatively close to 5 in that case, right? Because the instruction count for those high CPI instructions is so much higher than for the other class of instructions. This slide is just showing another way of illustrating what that weight would look out to, would wind up being. So to calculate the overall CPI, it would just be the CPI for a given instruction count multiplied by its relative weighting in the overall instruction count. The percentage frequency of that instruction class, that's what instruction count sub I corresponds to here, divided by the overall instruction count. And you will often see these questions about average CPI being given in terms of frequency. So for this example here, and this is also very much a textbook example here, it provides that for you. It says, for a given instruction type, of which it's broken down in sort of the R-type instructions or ALU instructions versus branches versus loads versus stores. I don't want you to get hung up in these questions and say, well, why is branch 2 and load and store 2? It's just a given. We don't have to design a processor that has that CPI. We're just being given those CPI just to be able to work out a homework question. Our actual processor will have its own CPI mix that we have to then either improve or just measure the resulting performance. So this type of question will give you for an instruction category, and those are the categories in the first column of this table. Here is the frequency of them, the relative frequency of those instructions for a given program. And here's the stated CPI for that instruction mix. So the question would ask, what is the average CPI for a given processor that has this characteristic? These can look a little abstract, I think. You're multiplying frequencies times CPIs to get a CPI times frequency value. I find that a little harder to work with than, instead of worrying about percentages, just make an assumption about what the overall instruction count is and do the math accordingly. Let's do this exact question first. We already know the answer is 1.5. Let's do this exact question where, instead of worrying about frequency values, let's make the basic assumption of, so for doing average CPI questions, this is just for me, I guess, and your approach may vary depending on how you like to reason about the arithmetic required for this. But for me, at least, when I'm calculating CPI, I find those relative frequencies very painful to work with. It's just easy to get confused. I'm not thinking in terms of real units anymore. I'm thinking in terms of percentages. So I like to assume n instructions, but for me, since you're oftentimes given the values in terms of percentages, I like to assume 100 instructions. And that would be my advice to you if you're ever facing an average CPI question in a homework or on a quiz or on an exam. Start by assuming that the instruction count is 100 total. And you say, well, it's not 100 total. We don't know how many it is. Okay, but we're given the value as a frequency. So the math should work out whether it's 100 or 1,000 or 10,987,654. The math should work out exactly the same because we are given a percentage. And you could argue that if my percentage is 6.43, then maybe it gets weird again if I assume 100 instructions, because that would mean I have 6.43 load instructions. But then make it out of 100,000 if making it out of 100 doesn't make as much sense to you anymore. But for me, this is a much easier way to reason about the question than worrying about the percentages in and of themselves. So the textbook chart will give, the frequency of that, but instead we could just break that down now in terms of actual instruction count. So for the ALU, we have the four categories in that example. There's ALU, there's branch, there's load and store, and brutal. And the book gave it, or the slide gives it in terms of percentages, and it says your ALU instructions are 50% of the time, and then it's measuring CPI times that frequency to get a 0.5 value, which that's, at least conceptually, that's where I find it can be somewhat confusing. What does that 0.5 correspond to anymore? If we're assuming there's 100 instructions, we don't have to worry about our frequencies anymore, and we can directly just convert that to some instruction count for that instruction class. So if we're told that ALU instructions are 50% of our instructions, and if I'm assuming there's 100 instructions in my total program, then I can get rid of the percentages entirely, right? Maybe this is just some fourth grade arithmetic, but these tricks keep me sane when trying to reason about these questions. If the instruction count is 100 total, then that's literally just saying that there's 50 instructions that are those ALU type instructions. 50% times 100 gets you your 50 instructions. The math is going to be exactly the same. I just think it's easier to reason about. The branches, right? The branches are 20%. So of our 100 instructions, 20 of them are branches. Our loads were also 20%, so 20 of our instructions are loads, and our stores are 10%. So 10 of them were stores. Just like the percentages would need to add up to 100% in the previous example, our total instruction count should add up to 100 here as we do it here, because I'm telling you there's 100 instructions. That subcategory should also then add up to 100. And then instead of worrying about some frequency times CPI, we don't really have to overthink it, I think, at this point. We can now say, well, we now literally should know for every 100 instructions, we should know exactly how many cycles are being spent on those. We do have to go back to that column in the table that I've not added here, but that's our CPI value for that instruction mix. Our ALU instructions, our R-type instructions, take 1 cycle. The other ones take 2. So we can consequently just calculate that out. If we have 50 ALU instructions, that's our instruction counts for the ALU type, this should take exactly 50 cycles. We have 20 branch instructions, each of which take 2 cycles. That should be 40 cycles. We have loads that take 20 that are 20 instructions, each of which take 2 cycles. That should be 40 cycles. We then have 10 store instructions, each of which take 2 cycles. That should be uh, 20 cycles for that. So the question's asking about average CPI for this instruction mix, and now I think it's pretty straightforward personally. We know that there is exactly 50 plus 40 plus 40 plus 20, 150 cycles to execute that instruction mix. And as a given, as we've sort of reframed the problem in terms of 100 instructions, our instruction count is 100. Carry the 7. All right. So we get 1.5 for our average CPI for that case. It's the same answer. So the textbook way of doing it is also completely correct. It should give the same answer. Um, but to me at least, now if I want to ask follow-up questions about this, so the follow-up question here is what fraction of the time is for data transfer? There was a homework question that kind of sort of asked about that as well, right? So data transfer is just a common way of referring to our load and store operations, right? Everything is transferring data, so I understand why that's a little ambiguous. But when the textbook or homework or a quiz asks about data transfer, it's referring to data transfer to our data memory. Yes, the whole thing is data being transferred, but in this case, transfer from memory to and from the register file. So the question asks what percentage of our time, what fraction of our time is spent in data transfer? Yes, you could go back to this weighted frequency table and answer the question. But if we go back instead to our whiteboard version of it, what fraction of the time is spent in data transfer? Well, we have 150 cycles, of which 60 of those cycles are spent in data transfer. So the answer would just be, 60 over 150, right? 40% of the time. At least to me, that winds up being an easier way to reason about this style of question. Because that'll be the case. That'll be the style of question you will get, which is here's our CPIs and our instruction counts, given generally as frequencies. What does it mean to do this, or what does this optimization change when we look at it this way? And if we think of it in terms of not percentages, which are kind of an abstract thing, um, versus in terms of let's execute 100 instructions from this mix, you wind up with answers that are back in our units that I think make a lot of sense for this. So this would be an example of a slightly trickier version of the same question because it's asking you to connect. So the previous question about data transfer, that was a semantics question. Do you know what data transfer means? And then the question becomes trivial. This question is asking, what is the impact of the MIPS displacement-based memory addressing mode? That's a mouthful, right? So what is the impact of having these loads and stores that also allow us to do that add operation as part of it, right? That allow us to take constant offsets and do an addition to our base register. The assumption is if we didn't have to do that addition, our load and our store operations would potentially take less time. So you can answer that certainly in a very high level sense of, well, if we didn't have this, we would need to have more add instructions, and a certain amount of the time we would need to have more add instructions, so our instruction count would potentially go higher, et cetera, et cetera. This question actually gives you that information needed to actually come up with a quantifiable answer. If we assume 50% of the MIPS loads and stores for our instruction mix have a zero displacement, how would that impact our overall performance if we weren't to have that displacement based memory addressing mode, and instead we're just to use additional add instructions every time, or add immediate instructions every time? to add that displacement back to our base register. I don't want to give the answer to this. I'd like you to think about this a little bit. And my goal for Friday is Friday Fun Day. Um, but we may not get to it. Maybe it'll be half Friday, half Monday, fun day to kind of cover some of that, what I wanted to cover on Friday. There is still one more big picture concept that's fundamental to understanding computer architecture that I would not be doing my job if we don't get to for this. So let's leave things here for today. I'd like you to think about this question between now and Friday. It's also going to be a homework question, so you'll get a chance to look at it again. Um, Based on what we know about the performance equation, what is the impact of having that displacement-based memory addressing mode? What is the impact of being able to add and subtract constants as part of the load and store word instructions? Again, we can answer that in a very high-level sense without knowing anything about this table. But with this table, as well as the secondary consideration of 50% of our loads and stores for a given application, we're just being told have a zero displacement. I'd like you to think about that a little bit between now and Friday, and we can quickly discuss on Friday, as well as our final quote unquote sort of big picture concept for this performance lecture. Let's leave things here for today. I'll stick around a little bit if everyone wants to chat. And otherwise, starting your group work this week, good luck. Let your TAs know right away if something is not functional with your group. Otherwise, we are going to sort of try to hold you to those project contracts you came up with. You can revise those now if you would like to. You're not required to. But good luck with your group. Having that other person or people there with you should help with the workload. Project Part A, you have 2 weeks to work on, and it should be doable within that 2-week time. Otherwise, if there's no other questions, I will see everyone on Friday for hopefully some Friday, quote unquote, fun day. Thank you.